Okay, good afternoon. Hope everybody's doing okay. I'd like to start almost immediately. And I know that you're accustomed to me using Google Meet, but I've decided to switch over to Zoom for now, and hopefully everybody is okay with that. I'm not sure what your other teachers are doing. I'm assuming that everybody else is using Meet, but for me, I find that Zoom works better for many things. Okay, so excuse me. I am going to get right into the stuff we're doing today on algebraic vectors. We've been doing a lot of stuff with geometric vectors. And by the way, I'm going to remind you that one of the things I really like about Zoom is the ability for you to interact with the rest of the class and to me as we go through this. So I'm going to be asking you questions from time to time. And I'm going to pause at that point, give you a chance to really sort of look at the material, review it, and give me an answer privately. So you're not going to broadcast it to the class. You're just going to put your answer in privately, and then we'll talk about the answers after I've had a chance to see what other people have to say. Okay, all right. So algebraic vectors. How are algebraic vectors different from geometric vectors? Everything we've done so far has been geometric vectors. The main difference, if I'm going to get the thing started now, is that with an algebraic vector, you have to have a Cartesian grid behind it. So you're going to have coordinates in the way that you're accustomed to seeing a Cartesian grid with X and Y coordinates. So we're going to be looking at position vectors in algebraic vector in an algebraic vector framework. But because the world is not just two-dimensional, none of us lives in a two-dimensional world. We're going to have to deal with a three-dimensional world as well. So we're going to be looking at position vectors in what is called R2, which is two-dimensional, kind of what you're accustomed to, but also looking at vectors in R3, which is three-dimensional. So we're going to recognize that the three coordinates in R3 form what we call a right-handed system, and we're going to understand what that means. I'm going to represent vectors in R2 and R3 using pairs or triples of real numbers. All right, so that's the gist of what we're going to be looking at today. So let's get started. First thing is, I'll just read what's on the screen, but you can read it for yourself. The coordinate system for R3 has an x-axis, a y-axis, which you're accustomed to. We're now going to add to that a z-axis. And these are oriented to form what's called a right-handed system, which means that if you point, you can see my diagram down here. If you point, let's move this out of the way a little bit here. If you point your index finger along the positive x-axis, so if you can see where my cursor is, your index finger is pointing along what we'd normally call the x-axis, and you curl your fingers in the direction of the positive y-axis. So that's your positive y-axis here. So this is the x and the y-axis. Then your thumb will point upwards, and that's your z-axis. So generally we refer to it as the YZ plane is the plane that is your piece of paper. So if you're looking at the screen right now, the YZ plane would be the piece of paper that you're looking at, and the x-axis is kind of coming out towards you. You kind of have to picture it that way. And if you look at the diagram I have over here, you'll see exactly, this comes from a website called GeoGebra, and you'll see that it has that basic format. So the x-axis is the one that's pointing out towards you. The z-axis is going up and down, that's the vertical axis. And by the way, the x-axis is positive on the side that's coming out towards you and negative on the other side. The y-axis is positive on the right, negative on the left. The z-axis is positive at the top and negative at the bottom, which is what this is showing. I'm going to do a little animation now to kind of give you an idea what that might look like. So I'm just turning this around so you can kind of see what a three-dimensional look of this x and y axis might be. All right, so if you want to see something looking like this, you can use the GeoGebra, and one of these classes I'll probably walk you through how you can use GeoGebra, a website that creates images like this in 3D. So there you go. It's a three-dimensional world that we're in now. We're going to do R2 and R3. So we're going to do two-dimensional and three-dimensional, but two-dimensional is something you're very accustomed to. But this is what a three-dimension looks like, and these are the axes right there that we just talked about. Let's move on. Now, a position vector, the definition of that is that it's a vector whose, remember, we're now putting everything into a Cartesian grid. So position vector is a vector whose tail is at the origin. As you can see here, I have two position vectors on the screen. And the head is located at some point in the coordinate system. So this vector A that I'm pointing to here has its tip at, or head as we call it sometimes, at 2, 5. So the point is a point 2, 5. The vector, the position vector, runs from the origin to the point A, but the vector itself is this whole line pointing in this direction away from the origin towards the point A. So there's an A, lowercase a, which is a vector, and an uppercase A, which is just a coordinate, which is at 2, 5. I have another coordinate over here, which is at -3, 2. Again, we're just restricting this to a three-dimensional world for now. And that point has a vector, a position vector, leaving from the origin and going to the point at B. So the coordinates of B are -3, 2, but the vector runs from the origin to the point. So lowercase b here for the vector, uppercase for the point. And that's really all there is to it. So in R squared, we denote such vectors as lowercase, and you can refer to it by the point that it terminates at the head of the vector. And in this case is -3, 2. In this case, it's 2, 5. Okay, so that's all that is. And again, very familiar to you because you've worked in a two-dimensional world for quite a while now. Let's continue. Now, we got to get into a three-dimensional world. In 3 dimensions, before I even animate it, again, I have the x-axis coming out towards you. So think of this thing, this x-axis that I'm pointing to here, the positive side of the x-axis, as moving out of the page. This on the other side is the part that's going into the page. And then the green line represents the y-axis, all right? Left is the negative side, the right is the positive side, and the z-axis is the part above the plane, the xy plane. And you can see it's dotted below here because the idea that GeoGebra, when it's demonstrating a vector, or a line I should say, is that anything below the plane tends to be dotted. We'll talk about that some more in a minute. But here's a vector, vector A. This black line represents vector A, which terminates at the point 1, 4, 5. Now notice that it's 1, 4, 5, which means I have an x coordinate of 1, a y coordinate of 4, and a z coordinate of 5. Now, I'm going to animate this a little bit. It's maybe a little difficult for you to see the 1 and the 4. So it's 1 along the x-axis, 4 along the y-axis, and 5 along the z-axis. So let me animate this a little bit. So hopefully that will make it a little bit more clear to you. All right, so I'm trying to show you that it does come out towards the 1 on the x and across to the 4 on the y and up to the z. Okay, trying to give you like a bit of a three-dimensional perspective on it. Hopefully that helps you to understand that. Okay, so there's a vector, right? A position vector again in R3. The point of the vector is this ABC triple, you know, an A of, sorry, the X of 1, the Y of 4, and the Z of 5. And the tail of this is at the origin. That's what makes it a position vector. All right, let's move on. Here's another position vector. And I kind of wanted to give you a little different perspective on this. So notice that this position vector is down here and it's a dotted line. And that's because you're seeing this below, this vector is actually below the plane that we're looking at. The plane is the XY plane, right? So this green line and this red line are the X and Y axis, and that creates a plane. So this gray area that you're looking at is referred to as a plane. So it's like a flat surface, a two-dimensional surface. So because we're looking below that two-dimensional surface, right, that's why this line is dotted. But here's another vector A, which has a 2 as the X coordinate, a -4, so it's at -4 on the Y, and it's at -3 on the Z. That's why it's below the line, because it's below the plane of the XY plane. Again, I'm just going to reorient that a little bit to give you a sense of the three-dimensional nature of this. Oh, sorry, didn't mean to do that. Let me go back. Let me try that again. Oh, sorry. So I'm just kind of moving it around so you can, and now when you see the bottom, now because we're going below the plane, you notice that the line was solid at that point, right? So those only dotted when you're looking above the line. So right now we're kind of looking a little bit below the line, and therefore that's why the line is now a solid line. Okay, all right, let's move on. Again, I'm just trying to give you an idea in a graphic coming from the GeoGebra website of what three-dimensional space looks like. Okay, now we can move on. To sketch vectors in R cubed, and we're going to focus more on R cubed because R squared is something that you're all, or R2, you're all well familiar with because you've been doing Cartesian grids from before high school. So we're going to, sometimes it's useful to sketch an R3 as a rectangular prism, right? So put the prism around that point that contains a point. So for instance, this point is ABC, right? They haven't given you specific values of A, B, and C. They're just saying that it's an A value for X, a B value for Y, and a C value for Z. And it's up here in this little section right here. That point represents the point. So this is vector P right here, right? And they've connected a line from the origin up to that point P. So this hopefully gives you some perspective on the sketch. What we're going to try to do now is answer some questions. And here's where you come into the picture, right? I'm going to do the first one with you. And then we're going to see if you can help me out with the others. Determine the coordinates of C, D, E, and F. So let's focus on the vectors, sorry, not the vector, the point C. That's a point in space. So I'm thinking, okay, to get C, I need a triple, because remember that any point in 3 space needs an X, a Y, and a Z. So I'm thinking, I'm looking at C right now. Well, I'm this far along the X-axis, and that would mean that my A value so my X value should be A, because remember, it's ABC that takes to this point right here. So if I'm this far along to get to this corner of this rectangular prism, then that A should be the coordinate of this C value as well, because I'm the same distance away from the X-axis going in, like coming forward, coming out of the page. So that C should have an X value of whatever A is, right? Same A as this one that's actually on the X-axis. So this C here should have an X value of A. Now let's look at the Y value now. Now for the Y value, I'm going to make reference to this line. Hopefully you can agree with me that if I'm looking at this C, that I haven't moved along the y-axis at all, right? Because my y-axis goes left and right. This C value hasn't moved along the y-axis, so that means my C value should be 0. But how about my when I say, sorry, I'm saying C value, my Y value should be 0. How about my Z value? Now for Z, if you look at this point, I am Z above the X, I'm this far above, I keep saying Z. I'm C above the X-axis, above the X-axis, going upward. So that means that my, whatever this Z value should be the same thing as this C value right here. So what does that all mean? My answer is A, 0, C. Okay, so A along this axis, nothing on the y-axis, but C on the z-axis. I'm hoping that makes sense. All right, so let's try this now. I'm going to ask you to private message me D, and I'm going to give you a hint, by the way, before you put your answer in. And this hint should help you out with D. Any point that's actually on an axis, and D is actually on an axis, by the way, that should be a clue. Any point that's actually on an axis, right, is sitting right on the z-axis, it should have zeros for every other coordinate except the z coordinate. I think I've given that one away, right? So I want you to go ahead now and give me your answer for the z coordinate, right? Give me your answer for the z coordinate. Anything you think it is, just put that in for me, please. As a text message, like I said, but just privately. So give me the, put it in brackets as usual. Interesting answers. I just, let me get 1 or 2 more and then I'll put the answer on. So give me an answer for the, you're some people already put more than 1. I just was asking for D. Okay. Some people are way ahead of everybody else. All right, okay. Just give me D for now, please. Just the D for now. And then we'll get to the E and the F later on. All right. Okay, so here's my D, which I think everybody got. All right, so 0, 0, C. And I did kind of give it away by saying that your other coordinates, X and Y, should be 0. And only one that you should have would be the C coordinate, the Z coordinate, and that's 0, 0, C. The E, which a lot of you have already given me, some people have really given me F as well, is the O or 0, BC. Okay, well done. And then the F, again, F sits on the x-axis, on the y-axis. That F is 0b0. Okay, it's just the x, it's just the y coordinate. It doesn't have an x, or it has an x, but it's 0, and the z coordinate is also 0. Okay, well done, very well done. All right, let's move on. Let's try this one. It asks us, I'm going to actually do part B first. In the following diagram, the point 624 is located in R3. So 624 is the red dot right there. What are the coordinates of A, B, C, D, E, and F? So I'm going to go through that again, but it asks us to draw the vector. Well, that's the easy part. I'm just going to put that in for you. Any position vector runs from the origin, which is at 0, 0, 0, up to the point. So there is my vector. The tail, the head at the origin, and the tail, or the tip, is at the 624 point. Okay, so let's just do it one at a time. Give me A. Remember, anything sit, and now we have not just A, B, C, we have numbers, right? We have actual numbers. So give me what you consider to be the coordinates of point A right here. Just give me A for now, please. Anybody, or everybody, I should say. Give me A. What do you consider to be point A, the coordinates of point A? And remember, use brackets. It's really the format is kind of good to have. Okay, give me a few more. Okay, good. So first answer, 600. How about B? Go ahead with B. And I'm not pointing to it. You can see it for yourself. Give me an answer for B now. Great, 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 great. Excellent. So there's my B. Okay, let's do C. Let's do them both. Let's do C and D, and then we'll do E and F. So C and D, give me both C and D. Very well done, by the way. Good stuff, good stuff. Excellent. Wow, I'm impressed. I'm genuinely impressed. All right. And finally, put in the E and the F now. I see like Andy jumped the gun. He's already put the E in, and he's already had the F, E and the F. Well done. This is not challenging you guys at all. I mean, this is fantastic. Okay, okay, good, good. All right, so let me put some answers in. So here's my C, which I think everybody got. We just look back at these answers. Yeah. Here's my D, which again, everybody got. Here's my E, and there's my F. Excellent, 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 excellent. Okay, so let's move on. All right, this is a little different. And I'm gonna give you some help with this one because it's not as obvious. But I think if I sort of start you off, you'll get an idea of how to answer at least the first question. The point Q is at 2, -3, -5, and it's shown in R3. So this is the point right here. Of course, we could also put a position vector from the origin down to that, but I didn't bother putting one in this time. It says write an equation for the xy plane. Now remember, this is my y axis. This is my x-axis. Think about those two together on a page, right? X and Y on a flat surface. I'm going to remind you, let me take you back to grade 9 for a minute. Here is a Cartesian grid, a two-dimensional Cartesian grid. I put a line here, which is superimposed on the x-axis, right? But this line had an equation. What was the equation of that line? Does anybody remember the equation of that line? Right? This line, yeah, we call it the x-axis, but it has another name as well. Does anybody remember the name of the line? Absolutely. Well, not quite, not quite. It's actually this. It's a y equals 0 line. And let me tell you why it's a y equals 0 line. If you think about any coordinate on this line, minus 4, 0, minus 3, 0, minus 2, any point on, if you pick any point on this line, the y value is 0. So if you take any coordinate, this is minus 4, 0, this is minus 3, this is minus 1, 0. Any coordinate along this line has a y value of 0. So if I wanted to get an equation for this line, I would say it's just a y equals 0 line, because that is what consistently every single y value is. It's the same thing if I were to do a line which is superimposed on the y-axis. I would just call that the x equals 0 line. Why? Because take any point along this line, 0, 4, 0, 3, minus 2, 0, minus 3, 0. The consistent coordinate or part of the coordinate in both of these cases is that the x value is 0. So that's why this is the y equals 0 line. This is why this is the x equals 0 line. Okay, now let's apply that to this. The xy plane. This is my y-axis. This is my x-axis. Give me an equation. If you think about what I just said about this line representing the y equals 0 line and this line representing the x equals 0 line, one is the x-axis, one is the y-axis. Can anybody come up with what they think an equation for the xy plane, remember, is a flat surface, not a line. These are two lines, right? This is a plane. So these two lines together, right, are the xy plane. So think of the xy plane as being a flat surface, like a grid sitting on the table. And we need an equation for that plane. Can anybody think of what the equation of that plane is, right? What would be consistent about every single coordinate sitting on that xy plane? Can anybody think of what that might be? Right? There's an equation that represents that. It's not a point, it's a plane. It's not a line, it's a plane. So can anybody think of what that might be? Nobody has an idea of what that might be, what the equation of that line might be. All right, so let me tell you then. So z equals 0, plane. It's not a line, it's a plane. So z equals 0 describes a plane. Every single z coordinate, hopefully that makes sense. I'm just kind of trying to give you an idea of what that plane is. It's this surface, right? It's this plane. I'm not looking at the whole three-dimensional space right now. I'm just looking at the xy plane. So the x-axis and the y-axis sitting together on a piece of paper. At every single point on that plane, the z value is 0. Okay? Let's move on. Now, write an equation for the plane. I'm asking for another plane again, containing the points. So think about a similar kind of way to represent it, right? The xy plane was the z equals 0 line. Write an equation for the plane containing the points P, M, Q, and T. Okay, so let's point that out. So here is P, here is M, here is Q, and here is T. Looking at the coordinates of those points should give you a clue as to what the equation of that plane is. Now, that plane just doesn't have those 4 points in it. Those are just points that are on the plane. The plane goes further than that or farther than that. So these 4 points are on the plane. Ah, interesting. Interesting. I see one answer so far. Can anybody else give me an answer to that? What would the equation of that plane be? Just look at the coordinates, because the coordinates can kind of give you an idea of what the equation of the plane is. What do you think, folks? I see some other answers in. Okay. All right, so let me reveal it. It's a y equals -3. Right? Look at the 3 points on that plane. 0 minus 3 is 0, 2 minus 3 is 0, 2 minus 3 minus 5, and 0 minus... What's the consistent similarity between all 4 of these points? They all have the same y coordinate. The y is the one sitting in the middle. Every one of them had the same y coordinate. And if I were to extend that plane going up and down, right, forward and back, every single other point on that plane would still have the same y coordinate, which is that y is equal to -3, as long as you're sitting on that plane. So think of the 4 points here and extend that out in every direction. Every single y value is y equals -3. Okay, let's move on. But look at part C. Part C is asking for a description, a mathematical description of the set of points in a rectangle, PMQT. Now, if you look at P to M to Q to T, all of these points are on the same plane. Now, normally if we have a plane, then we would look for some equation that would generalize all the points on the plane. And that would just be y equals -3, the answer for part B. But they're restricting it to only points that are within this rectangle. That's what the question says, only the points on the rectangle. So we can start by saying that it is the x minus 3z where all the y values are -3, but the x values have to be between 0 and 2, and the z values have to be between -5 and 0. Look back at the box and see if that makes sense. Or y values are all -3. That's the same thing as the y equals -3 plane. But our x values, if you look at the x-axis, here's my x-axis right here. My x values start at 0 and go up to 2. So that's the reason for this part of the restriction on the domain. And then our z values, which is this axis right here, goes from anywhere from -5 up to 0. That takes care of that. And that's why part C has this answer. Part D asks for the equation of another plane parallel to the xy plane, but passing through this point. So that point is this point right here. So I need a equation of a plane parallel to, no, the xy plane, remember, is the x and y axis, and we already said that was a z equals 0 plane. But if we wanted to be parallel to a point which has this or these set of coordinates 0, 0, -5, wouldn't it make sense for that to be, oh, sorry, let me go back, to be the z equals -5 plane, because it's parallel to the plane of the xy, but also because it's down here, it's the z equals -x5 plane. And that's it. That's all. We're done. See you next time.